Hi, everybody. Welcome back to CS224N. So first, just a couple of announcements. Originally, this was going to be the day when assignment 5 was due, but as you've seen, we're giving you one extra day, so it's now due Friday at 4:30. We do realize that assignment 5 has been a bit of a tough challenge for many people, though we've been trying to help people out in office hours and otherwise. So I hope at the end of the day, it will seem like it was a really good learning experience to really get some much more kind of close hands-on look at how transformers work, rather than it simply being loading up a transformer as a black mystery box. After Friday, I guess there's no rest, since we do really hope that you can sort of basically immediately transition to working on final projects, since there's basically 4 weeks to go on final projects. And in particular, we're hoping to get feedback on your project proposals back by next Tuesday to help that process along, and people will be able to get started on them soon. And, you know, it's just maybe a good moment to say that, you know, we do really appreciate all the people who have been putting tons of effort into these assignments, and we like that sort of all the keenness we're seeing from the students. Okay, so with that out of the way, today I'm delighted to have giving today's lecture on neural language generation, Antoine Bosselut, who's at present a postdoc at Stanford. He's someone who's done a lot of work on natural language generation in his previous life as a University of Washington PhD student, and next year he's going to be taking up a position as a professor in Switzerland. Okay, so welcome, Antoine.
Thanks, Chris. That's a very kind introduction. It's great to be here giving this lecture at CS224N, particularly on one of my favorite topics in deep learning for NLP, natural language generation. And so hopefully by the end of this lecture, most of you will have at least learned a bit about NLG with deep learning, and hopefully be motivated to start doing some research on it, or launch a startup in NLG, or perhaps go work on it in a larger organization. Okay. So to start, I think it might be really helpful to define what we mean at a high level when we talk about natural language generation, because you know, over the last few years, the definition has actually sort of changed and has really grown as a subfield to really encapsulate any part of NLP that involves the production of written or spoken language. In other words, if you're given some inputs and your goal is to generate text to, you know, describe, respond, translate, or summarize that piece of text, you know, NLG really focuses on how you can actually build a system that can automatically produce a coherent and useful written piece of text for that for human consumption. And it used to be a much more limited research area, since many tasks that we now view as NLG problems didn't actually involve much text production prior to neural networks. But now that scope has expanded considerably, and we have this much larger area to sort of work in. Unfortunately, we're not, you know, quite yet at the level of the types of AI NLG tools that we've seen in pop culture and that we like to imagine. But we are starting to see many areas where NLG tools are having a massive impact. You know, to start with, machine translation is kind of the classical example of an NLG task. You know, these days, ever since the task moved to neural networks and an NLG framework around 2014 or so. And now we've seen a rapid improvement in the quality and applicability of translation systems. And in fact, you can often use Google Translate for most of your kind of retail translation needs as a good starting point. Similarly, NLG technologies really underpin some of the dialogue systems that you might interact with on a daily basis. Anytime you use, let's say, Siri, Alexa, Cortana, Google Home, Bixby, or pretty much, you know, any other major company's dialogue system, there's a good chance that there's a neural NLG component embedded in that system that's involved with providing you an answer to your query. And there's really still a ton of progress to be made in this area, and it's led to some major companies to actually crowdsource chatbot technologies from researchers and students such as yourself to continue to try to make big advances in this area. We're also, seeing lots of NLG technologies, used in areas such as summarization, where systems often have to aggregate information from potentially multiple sources and rephrase the most salient content in a shortened but still very engaging way. And while our go-to example for summarization is generally related to, let's say, generating news highlights, summarization systems have actually, achieved broad applicability in many areas where we ingest content, such as summarizing emails or summarizing meeting transcripts. And there's actually many more areas not listed here. I didn't actually put it on the slide, but a few months back, a tool called Semantic Scholar actually developed a neural system for generating summaries of scientific papers, which is something that I personally end up using quite a bit as an example of how humans can interact with these technologies. But these modalities aren't actually limited to text in or text out. So actually the classical NLG area that I mentioned earlier as how the task used to be framed was actually around what we now call data to text generation. So can you learn to compile or, let's say, summarize the most interesting facts from a table or a knowledge graph or some type of data stream? That way humans can get the most interesting and salient content that's being presented in these data structures rapidly and in an easier to ingest format than having to look through the structures themselves. We've also seen a lot of recent work in visual description that tries to use language to describe the content in images or videos. So around 2014 or so, we start to see the first neural NLG systems in the space, and they've really continued to mature in the last 6 years. And now we actually tackle much more challenging description tasks, such as generating full descriptive paragraphs of scenes, or generating streams of visual, generating descriptions for streams of visual content, such as in video captioning. And these tools have really broad applicability in different areas of AI. And finally, the last sort of application I kind of want to mention is that we've also started seeing NLG systems being developed in more creative applications, such as story generation, where AI systems can now help humans write short stories, blog posts, or even full books in some case as creative writing assistants. And in other areas such as poetry generation, we can actually have kind of full automated settings where you can have AI agents that can generate something like a sonnet, and in fact condition that on a lot of demands that are given through a user interface. And so, I hope that by this point, I've really given you a look into the breadth of NLG applications and how it sort of encompasses any task that you might think of that involves production of text. And each of these tasks, really requires, different algorithms and different models and a different way of designing the system to get right. But what they have in common is that a lot of them are powered by next generation advances in deep learning for NLG. And the goal of today is to really give you the introduction to these topics that really allows you to contribute to the next era of these technologies and in designing deep learning systems for NLG. And so I think to start, what might be interesting to do is to quickly recap topics that you may have seen in previous lectures, but which are going to be very relevant today when we're trying to design an NLG system. And what we're effectively trying to do in this setting is, take a sequence of tokens as input and produce new text that is conditioned on this input. And in what we typically call the autoregressive setting, which is the most common sort of text generation setting, we take these produced tokens of text and we feed them back into our model to generate the next token in the sequence that we want to generate. But so to really understand what's going on in an autoregressive NLG system, what we really need to start to do is look at what happens for the generation of an individual token, since further stages really depend on taking that generated token and passing it back in as input and doing the same thing. So what happens at a low level is that your model takes in this sequence of inputs, so these Ys, and it computes a vector of scores using the model itself. And each index in that vector corresponds to the score for a token in your vocabulary. So the only tokens that your model is actually allowed to generate. And then what you do is that you compute a probability distribution over these scores using what we call a softmax function to compute a probability estimate for each token in your vocabulary given the context that precedes it. And as a shorthand, I'll just mention that sometimes I'll remove the W from this probability equation, but just know that when I write out the probability of a token Y at time T, what I mean is the probability that Y of T is a particular word. So it's kind of a variable assignment. But so what actually is the output of what we typically call a text generation model at this put is actually this vector of scores, and then that vector gets passed to the softmax function to give us a probability distribution over the set of tokens in the vocabulary. And then to actually generate a token, we can define what we call a decoding algorithm. That is a function that takes in this distribution P over all the tokens of the vocabulary, and it defines a function for selecting a token from this distribution as the next token that is produced by our NLG system. And for that distribution to be calibrated in such a way that it means anything, we need to train the model to actually be able to do the task. And so the most common way of training text generation models is to use maximum likelihood training. And despite its name, we don't actually maximize likelihoods. We actually minimize negative log likelihoods. And what that actually is just a multi-class classification task where each word in our vocabulary is a class that can be predicted by the model. And so at each step in the sequence, we're actually trying to predict the class that corresponds to the word that comes next in the sequence of text that we're trying to train on. And this word is often called the gold or ground truth token, as just kind of interchangeable vocabulary that we use. And another term for this training algorithm is teacher forcing. So you might see these expressions kind of used interchangeably if you read papers on this topic. But so at each step, you're really computing a loss term that is the negative log likelihood of predicting this gold token Y1 at every step. So in these slides, whenever you see an asterisk next to a Y, that means that this is a gold token that comes from a training sequence. And you can do this for multiple steps, adding up the log likelihoods along the way. Eventually, you're going to arrive at the end of your gold sequence, and you'll be able to compute gradients with respect to this summed loss term for every parameter in your model, which allows you to update it so that the next time around when you see this sequence, your model is more confident in the probability that this sequence is a correct sequence, given the same context it has seen before. But most of this should just be a recap from previous lectures on language modeling and machine translation. But now that we've got that out of the way, let's get to the fun part and talk about some new topics. The first one of which is decoding, which is actually one of my favorite topics in natural language generation research. So if you recall, your decoding algorithm is really the function that takes in this induced probability distribution from your model over the next possible tokens that can be generated and selects which one of those tokens should be outputted. So once your model is trained, this distribution should be meaningful and you want to be able to generate a sensible next token. And then you can use these generated next tokens, so the blue Y hats here, as input in the next step of the model, which allows you to recompute a new distribution, decode a new token, repeat the process, and eventually end up with a full sequence that your model has now generated given a fixed starting sequence of text. And so let's talk a bit about the algorithms that we can use to decode tokens from this distribution. So you've actually already seen some of these in a previous lecture on neural machine translation, I believe, where you started off by seeing a relatively simple decoding algorithm that nonetheless remains very popular, argmax decoding. And with argmax decoding, you pretty much just take the highest probability token from your distribution as the decoded token and feed it back into the model to get the distribution at the next step. And you keep repeating this process, and it's very nice and it's very convenient. And you've also, I think, learned about beam search, where you can scale up these greedy methods by doing a wider search over the set of tokens that follow, the set of most likely tokens that follow, to try to find a subsequence that has a lower overall negative log likelihood, even if in the intermediate step, it tends to be higher than what would be the argmax decoded token. And while these greedy methods work great for machine translation and in other tasks as well, such as summarization, they do tend to be problematic in many other text generation tasks, particularly ones that end up being more open-ended. So one of these big problems that they have is that they often end up repeating themselves. So here in this example from Holtzman et al. 2020, we can see that after around 60 tokens or so of generation, the model really devolves into just repeating the same thing over and over again. And this actually tends to happen a lot in text generation systems. Repetition was actually one of the biggest problems that we tried to tackle in text generation for many years and still face to this day. And I think it's worth taking a look at why repetition happens from a bit more analytically, so that you can perhaps better understand the interaction between your model and your decoding algorithm. So just as a quick little visual demonstration, here I'm showing you the step-by-step negative log likelihoods from two different language models, one based on recurrent neural networks and one based on a transformer language model called GPT. And I'm showing this plot for a particular phrase, I don't know, which for anyone who's worked in chatbots has probably seen many times, potentially even in nightmares. It's not a very interesting plot, though. What we do see is that the transformer model does tend to be a bit less confident in the probability of each word than the recurrent neural network does. What's more interesting, though, is what happens if I repeat this same phrase multiple times in a row. And one of the things that we notice here is that the repetition of this phrase actually causes the token level negative log likelihoods to get lower and lower for each of these tokens, which actually means that the model's becoming more confident that these are the right tokens and that they should probably follow the preceding context as we generate it more times. And this doesn't really subside as the sequence gets longer and longer. As you keep repeating the same phrases again over and over again, the model becomes more and more confident that the next time around it should say the same thing. And while this actually kind of makes sense, and that if you say the phrase, let's say I'm tired 15 times, it's a fair bet that on a 16th time you're actually going to say it again. It's not necessarily the behavior that we want our generation systems to get stuck in. Another interesting thing to note here as an aside is that this behavior is actually less problematic in recurrent neural networks than in transformer language models. So you can see that for the LSTM, the curve flattens after a certain point. And so if you remember in perhaps a previous lecture on why we might like transformer language models, one of their benefits is that they don't have the temporal bottleneck of tracking a state, which a recurrent neural network tends to have. And so the removal of that bottleneck actually ends up making them more prone to repetitive behavior when you use greedy algorithms to decode. But so what can we actually do to reduce repetition, since it's a pretty big problem in these systems? Well, there are actually quite a few proposed approaches in the last few years, some of which I'll summarize here, which range from the kind of hacky but surprisingly effective don't repeat any n-grams at inference time. But there's also been training time approaches to do it, such as having a loss function that minimizes the similarity between hidden activations at different time steps, or a coverage loss that penalizes attending to the same tokens over time. So if you change the inputs that your model is allowed to focus on, it's naturally going to produce different text. Or more recently, an unlikelihood objective that actually penalizes outputting the same words, which we'll talk a bit more about later. But the truth is that the problem here really lies in using greedy algorithms in the first place. In many applications of human language, humans don't actually speak in a probability maximizing way. So if you look at this plot from Holtzman et al. 2020, it shows the per time step probability of human written text in orange and beam search decoded text in blue on the same graph. And what you can see is that beam search decoded text tends to be very high probability with little variance over time. And this makes a lot of sense, because it's literally trying to maximize the probability of the sequences that it produces. And a big part of that is maximizing the step-by-step probabilities of the tokens that it uses. But meanwhile, we can see that human written text is a lot more variable, often actually dipping into very low probability territory. That actually makes a lot of sense. If we could always predict human text with high probability, there'd really be no reason to listen to each other speak, since we'd know what we were going to say. But so ultimately what we want to be able to do is to match the uncertainty of human language patterns in how we decode text, which is why in many applications that tend to have this higher variability, sampling from these distributions has kind of become a go-to decoding method, particularly in creative generation tasks. And so with sampling, we take the distribution over tokens that's produced by our model, and we generate a token randomly according to the probability mass that is assigned to each potential option. So rather than doing any type of greedy step, we use the probability on each token to give us a chance that that token is generated. And so this does allow us to kind of get much more stochasticity in the types of tokens that are generated. But a challenge that pops up here is that these distributions tend to be over a very large vocabulary. And so even if there's clearly tokens that have a higher chance of being generated, the tail of the distribution can often be spread over a much larger number of possible tokens. And so this becomes a bit of a problem, because these tokens in the long tail are probably completely irrelevant to the current context. So they shouldn't have any chance of being selected individually. But as a group, it ends up that there's a decent chance that you could output a completely irrelevant token. Even if 90% of your probability mass is on relevant tokens, that means that you have a 1 in 10 chance of outputting something that completely throws off your entire text generation pipeline and is completely inane. So to mitigate this, the field has developed a new set of algorithms that tries to prune these distributions at inference time. And so top K sampling is kind of the most obvious way to do this. So here we recognize that most of the tokens in our vocabulary should have no probability of being selected at all. So we just truncate the set of tokens that we're allowed to sample from to be the K tokens with the highest amount of probability mass in the distributions. And common values of K are often 5, 10, 20, sometimes up to 100. But really, it's a hyperparameter that you end up setting as the designer of this system. In general, though, what's important to note is that the higher you make K, the more you'll be able to generate diverse outputs, which is good because that's what we're trying to do. But you're also going to increase the chance of letting that long tail seep in and generating something that's completely irrelevant to the current context. Oh, sorry. Meanwhile, if you decrease K, your outputs are going to be safer from these long tail effects, but your text may end up being boring and generic because your sampling algorithm starts to look a lot more greedy in nature. And this kind of shows the problem of having a fixed K as the number of tokens that you can generate from your distribution. If your distribution at a certain point is pretty flat, such as in this example, she said, I never blank, you might not want to truncate a lot of interesting options that, using a small value of K when there's so many good choices that could fit in this potential context. Conversely, in a different example, you might want to cut off much more than, let's say, your minimum K options because only a subset of them end up being quite suitable. And, a higher K than is really necessary lets that long tail seep in and potentially, ruin your generation. And so, in response to this, top P or nucleus sampling is a way around this issue. So here, instead of sampling from a fixed number of tokens at each step, you sample from a fixed amount of probability mass. And so depending on the flatness of your distribution, you end up including a variable number of tokens that is kind of dynamically changing depending on how that probability mass is spread across the distribution. And so, to kind of describe this visually, if you have, 3 different distributions at a particular step to generate a particular token, they're each going to prune a different number of tokens from the available set that you can sample from, depending on what the value of P is and what the peakiness of that distribution actually ends up being. So, I keep talking about this concept of flatness of a distribution being kind of critical in understanding how many tokens we can actually end up sampling from. And in fact, as we try to use sampling algorithms, we might find that the model that we've learned may not actually be producing probability distributions that lend themselves very nicely to using these types of sampling algorithms. The distributions might be too flat, they might be too peaky. And in fact, what we might want to do is rescale those distributions to better fit the decoding algorithm that we might want to use. And we can do this with a method that's goes by a variety of different names, which I call temperature scaling. And here what you do is that you apply a linear coefficient to every score for each token before you pass it through the softmax. That temperature coefficient is the same for every token, so it's not dynamically changing amongst your vocabulary. It stays the same. But what happens is that change ends up being amplified by the softmax function. And what ends up happening is that if your temperature coefficient is greater than 1, you're actually going to make your probability distribution much more uniform. In other words, you're going to make it flatter. Meanwhile, if your temperature coefficient is less than 1, these scores are going to increase, which is going to make your distributions more spiky and make the probability mass kind of be pushed towards the most likely tokens. One last thing to note about temperature is that it's not actually a decoding algorithm. It's just a way of rebalancing your probability distribution. So in fact, it can be applied to all of the sampling algorithms I described before and some greedy decoding algorithms as well. The only one whose behavior is not affected by softmax temperature scaling is argmax decoding, because even though you change the relative magnitudes of the probability mass in your distribution, you don't actually change the relative ranking amongst tokens in that distribution. So argmax decoding will give you the exact same output as before. But now that we're thinking about how we might, change the distribution that's produced by our model, we might realize that we might want to change more than the relative magnitudes I mentioned, and also instead change how they're ranked with respect to one another. Maybe in fact, our model is not a perfect approximation of what the distribution over tokens should be. Perhaps the training wasn't done right, or we didn't have enough training data to actually make it well calibrated. And so if we decide that our model isn't well calibrated for the task that we're doing, we may want to bring in outside information at decoding time. And so here I want to talk a bit about new classes of methods that let us change our model prediction distributions at inference time rather than relying on a fixed static model that's only been trained once. And a cool way of doing this that came out last year is to actually use k-nearest neighbor language models, which allow you to recalibrate your output probability distribution by using phrase statistics from, let's say, a much larger corpus. And so, what you do in this method is that you initialize a large database of phrases along with vector representations for those phrases. And then at decoding time, you can search for the most similar phrases in the database. And so what you do is that you take the representation of the context that you have from your model, and you compute a similarity function with all the representations of the phrases that you have stored. And based off the relative differences amongst these different phrases to your current context, you can compute a distribution over these most similar phrases. And then you can take the next tokens that follow these phrases and add the statistics around those phrases to the distribution from your model. And so this allows you to really rebalance the probability distribution that your model has given you with this induced distribution over phrases, and interpolate them together to get a different estimate of how likely certain words are.
So Antoine, one question right now is, how do you know what to cache?
Yeah, so that's a really good question. I guess, the answer there is that you could probably, decide on what might be a salient set of phrases, depending on, let's say, named entities that you might be interested in, or phrases that that your model's distribution doesn't handle very well. But I'm pretty sure in this work, they took every phrase in their training corpus, cached it, and then relied on very efficient algorithms for doing this search over representation similarity to actually find the most likely ones. Though they did prune the number of phrases that they actually used to make this distribution, the phrase distributions, that it wasn't over the entire corpus. So it's fantastic that we can now rebalance these distributions if we find that our model is doing poorly. For particularly, this might be relevant if, let's say, we're jumping into a new domain. So we've trained a nice big generation model to on Wikipedia text, and now we're going into something that's more linked to stories. We might want to use this type of system to get distributions from phrases from there. But it's also possible that we may not always have a good database of phrases to help us calibrate output distributions for all the types of text that we want to generate. And so luckily last year there's also been new approaches that look at doing this in a gradient based way. And so the idea here is that you can actually define some type of external objective using a classifier that we typically call a discriminator. But in this figure from the paper that proposed it, they called an attribute model. And what that classifier does is that it approximates some property that you'd like to encourage your text to exhibit as you decode. So perhaps it's a sentiment classifier because you are working on a dialogue model and you want to encourage positive sounding comments. So then what you do is that as you generate text, you input the output of your text generation model to this attribute model, and there's some tricks on how you should do that in order to actually not have it be a discrete token that you provide to the model, but instead a distribution over tokens. But the important thing is that if you do this the right way by using the soft distribution of tokens as inputs to the attribute model, it's going to be able to compute a score for the sequence that it receives. So that if it's a sentiment classifier, it can evaluate how positive of a sequence you provided to it. And then what you can do is that you can compute gradients with respect to this property and back propagate those gradients back to your text generation model directly. But instead of updating the parameters, which is what you would do during training, you instead update the intermediate activations at each layer of your model, which you can then forward propagate to compute a new distribution over the sets of tokens. And so it's a neat trick that allows you to do real-time distribution updating based on some outside discriminator that's allowing you to update your internal representations of the sequence such that it hopefully generates something more positive at the output in this case. So these distribution rebalancing methods, either based off nearest neighbor search or on using some type of discriminator, are quite promising and interesting. But they also end up being quite computationally intensive. In the first case, you're essentially doing a search over thousands of phrases to rebalance your distribution. In the second, you're doing multiple forwards and backwards passes at every step to try and make the tokens exhibit a particular behavior more. And unfortunately, neither of them actually stop you from decoding bad sequences either. It's possible that even after you rebalance your distribution, you're still generating something that looks terrible. So in practice, something that we often use in text generation to improve our sequence outputs are what are called re-rankers. And so what we do here is that we actually decode multiple sequences, perhaps using sampling or a wider greedy search, say maybe 10. And then what we can do is that we can initialize a score to evaluate the sequences we produce and re-rank these sequences according to the score. And the simplest thing we can do is to actually just score them by the likelihood given by the model, for example. Especially if we're using a sampling algorithm, we might want to make sure that we didn't generate something that totally deviated from good text, which would tend to have a very high perplexity. So this perplexity is perhaps a good re-ranking function. It's just important to be careful as well that, remember, repetitive sequences tend to have very low perplexity as well. And so if you rank by perplexity, you're likely to just generate something you were trying to avoid in the first case. But we can also make our re-rankers evaluate more complex behaviors. So in the same way that we could use gradient-based methods to update our distributions to exhibit more complex behaviors, we can actually just take those same attribute models and use them as re-rankers to re-rank a fixed set of sequences rather than have them back propagate gradients to the main model. And so we can use them to rank things such as style, discourse, factuality, logical consistency. But just be careful if your re-ranker ends up being poorly calibrated. Just because you've trained a classifier to predict whether a sentence makes a factual statement doesn't actually mean that it will be good at ranking different factual statements with respect to one another. And finally, a nice thing about re-rankers as well is that you can use multiple re-rankers in parallel if there's multiple properties you want to score, and come up with, let's say, a weighted average of different ranking scores to decide on what might be the best sequence according to different properties. But so, to recap what we've talked about in terms of decoding, I want to mention that decoding is still a very challenging problem in natural language generation that we haven't really figured out yet. Our algorithms still don't, really reflect the way that humans choose words when they speak. And our best approaches, are currently based on trying to calibrate probability distributions produced by models to perhaps be more representative of human likelihood. But the truth is, the human language distribution is quite noisy and doesn't reflect the simple properties that our decoding algorithms often capture, such as probability maximization. But different decoding algorithms do allow us to perhaps inject biases that encourage different properties of coherent natural language generation. That's allowed us to make promising improvements in this area as well. And in fact, some of the most impactful advances in NLG over the last few years have really come from simple but very effective modifications to decoding algorithms, because you can often have impact across a very large number of tasks by making a good change to a decoding algorithm. But really, there's still a lot more work to be done in the space, and hopefully, many of you will be the ones to make these next breakthroughs. I'm happy to take questions at this point if any have popped up.
Well, here's one question. How do you evaluate, how do you tell whether rebalanced distribution is better? And if I editorialize from there, I guess you're admitting on this slide that you can't just look at the probability.
Yeah, so yes, you can't just look at the probability. I mean, there is a certain amount of trust that happens, that if you don't trust that your ranker is giving you a better assessment of whether you've produced a quality piece of text, perhaps you shouldn't be using that re-ranker in the first place. And hopefully you've actually means tested that re-ranker to actually show that it has that it improves the quality of text. But we're going to talk a lot more about how you can actually evaluate the quality of text later on. Though I should warn you ahead of time that the answers are not as direct and complete as you might want them to be. And in fact, there's a lot of room for interpretation in how you would actually do that.
Maybe you should go on about that later, but I guess people are puzzled on that because there's another question that's asking or saying that you said you don't know how to make a model choose words like a human. How do we model different humans from different backgrounds, etc.?
Yeah, that's a really good question. The answer to that is that you could potentially try to do kind of fine tuning on the language distribution of a particular human, starting from, let's say, a pre-trained language model, since you'll probably never have enough data to only use a single human's outputs. Or you could try to do some of these rebalancing methods that we've spoken about to perhaps use those to actually make your distributions approach a particular human's language distribution more closely. So in the gradient-based methods that I described, I could perhaps train a single language model only on my type of language, even if I have a much larger one that's trained on a much larger corpus of language from different speakers, but then try to make it so that my model ranks the outputs of the main model.
I've got a question.
Yep.
So nucleus sampling and top case sampling are really effective in practice. And you made the argument that there are all these little tiny things with very little probability mass, but it sums up to more probability mass. But if it sums up to more probability mass than they actually should have under the real distribution of human language, shouldn't our models have been trained to put less probability mass on them? And so why aren't our language models better in that case? Like, why do we have this issue if they actually are getting more probability than they should?
Yeah, that's a really good question. I think the answer to that is that the way we train them, which I'll get to in a bit, is really trying to model the distribution of human language as it sees it in its training corpus. And it's actually surprisingly effective at doing that. But at the same time, when we actually start to use these language models out of the box in the NLG tasks that we work with, first of all, there's always slight deviations in the distribution of text that we're actually trying to model for the task we're doing, and what the large corpus we trained on was in the first place, which can make these decoding algorithms less effective. And the second thing I would note is that even though these decoding algorithms are quite effective in practice, they aren't doing what humans do when we speak. We're at no point when a human speaks are we potentially trying to maximize the probability of a potential next token or randomly select a word amongst a set of tokens. We ultimately have world models that drive how we select the tokens that we choose to say in order to make our points. And that's very different from what we get in probabilistic language models. Now, should we throw away probabilistic language models? No, because as you mentioned, they end up working quite well. But at some point, we also do need to mitigate these differences between how humans end up speaking and how language models end up modeling language.
Thanks.
So now that John has primed us perfectly for what comes next, let's jump back into to training these models, because the pipeline that I framed earlier being you train your model, then you choose your decoding algorithm. Depending on properties you're interested in, is great. But the truth is there's interactions between your decoding model and your training algorithm that you might want to be thinking about during training, which is not really what we're doing right now. And so if you recall, the training algorithm that we've proposed up to this point is one where we just try to minimize the negative log likelihood of the next token in a sequence, given the preceding ones at every step. And as I mentioned, this actually works pretty well for training autoregressive models of human language, but it actually causes a few issues, which John hinted at. So in the next few slides, I'm gonna talk a bit about these issues and then highlight some training solutions to these problems that I found interesting or that I think are important from the last few years. So the first issue is actually one that I hinted at in the last section. Which is that training with maximum likelihood tends to discourage textual diversity. And I showed this sequence on a slide earlier as an example of greedy algorithms being prone to generating repetitive sequences, which is just about the worst form of diversity that you could get. But greedy algorithms are just trying to maximize the probability of the sequences that they produce. So it can really only be prone to repetitive and undiverse phrases if those phrases are scored highly by the model to begin with. And that ends up being one of the issues with maximum likelihood training, is that it tends to end up favoring generic expressions because those are the ones that are often the most likely in human language production. But as we all know, and as I mentioned earlier, human language production isn't about maximizing the likelihood of the words that we produce. So even though we might produce generic phrases more often than ungeneric phrases, that's not the goal that we're setting out with when we speak. There's a lot more to communication that really isn't synthesized by a training objective that tries to maximize probability over the human language that's being read. So how can we end up mitigating this problem? So an interesting approach that I really liked that came out last year was actually proposed by Wellick et al., which was called unlikelihood training. And so here, what you do is that you actually discourage the production of particular tokens by the model in certain contexts. And so what happens is that this loss term here decreases as the probability of the Y-neg tokens decreases. So for any token that you don't want to generate, as the probability of generating that token goes down, so does the loss term, which means that you're not actually updating the model as much for this particular behavior. What's important though is that you still have your t-shirt forcing objective. So what's going to happen is that the model is going to learn to capture both the distribution of language from the training corpus, which it needs to do to learn how to generate text, but also it's going to learn how to not say particular words that you might not want it to. And then what you can do is that you can set this list of words that you don't want the model to generate to actually be words that you've already generated before. And so in essence, you're teaching the model to not say the same things again. And that's just naturally going to limit the amount of repetition that your model is going to be able to spit out, and you're going to be able to generate more diverse texts as a result as well. But a second and very important issue that comes from training with maximum likelihood is what we often call exposure bias, which is that the context that we train on to generate the next token are going to look different from the ones that we see at generation time. And so why might that be? Well, so what happens during training is that we always get a token from a gold document or human text as input. It's the gold sequence, as we call it. But then during generation, we're feeding our previously generated tokens back into the model as the input, rather than these teacher force tokens that are from the gold documents. And so that set of tokens is actually quite affected by things like the distributions produced by our model and the decoding algorithm we use to get tokens. And so, can this end up being a problem? Well, yes, because as we've seen before, the types of text that our model generates are often, not a very close approximation of human language patterns in the training set. And so there's going to be an imbalance between the type of text that our model has learned to predict, predict and to expect to see, and the type of text that it will see once we actually start decoding. And so once your model starts receiving its own inputs, which are going to deviate from the distribution of text it expect, it's going to be very challenging for it to be able to generate coherent text going forward, because it's not going to really know how to synthesize its own information that it's generated. And so there's a variety of ways to try to counter this exposure bias issue, and many more that continue to come out. Unfortunately, there's not really enough time to talk about all of them, so I've added slides to discuss two of them that are based on semi-supervised learning here. But I really want to focus more on two other approaches that I personally find very interesting. The first is called sequence rewriting. And so, in this setting, your model first learns to retrieve a sequence from an existing database of human written prototypes. So it's kind of like our nearest neighbor decoders earlier, where we cached a bunch of phrases. Here, you cache a bunch of sequences that might be similar to the one that you're supposed to produce for this new situation. And then what we do is that once we take this sequence and retrieve it, we learn to edit it by doing things like adding, removing, or modifying tokens to more accurately reflect the context that we're actually given, rather than the one that this original sequence was designed for in the first place. And so we can still use an algorithm here that tries to maximize likelihood for training, but because there's this sort of latent variable of retrieving the right prototype that's involved, it makes it less likely that our generated text ends up suffering from exposure bias, because you're already starting from something that looks more like a training sequence that you might have seen. Another general class of possibilities we can do is to let our model learn to generate text by learning from its own samples. And this naturally maps itself nicely to reinforcement learning, which is actually one of my favorite ways to learn how to generate text. In this setting, you're going to cast your text generation model as a Markov decision process, where your state S is the model's representation of the preceding context that you see. Your actions A are the words that can be generated. Your policy is the decoder, and your rewards are provided by some type of external score. And here you can learn many different behaviors for your text generation model by rewarding it when it exhibits those behaviors. And so to kind of quickly join this framing with the perspective of the text generation models that we've seen so far, you're going to be taking actions by sampling words, hat Y from the distribution, and then you're going to feed them back into the input to get a new state, which is what we've been doing at every point. What's different though is that as you generate text, you're using some external reward function to compute rewards for each token that you generate. So you're rewarding every action that you take. And then you scale the sample loss on this particular token that you generate by this reward, which is going to encourage the model to generate the sequence in similar contexts if the reward is high. So to put it very clearly, you're minimizing the negative log likelihood of your sampled token. So here it's not a gold token. Notice the hat that is on the Y expression in the reward function. And then you're going to compute a reward for that token and scale this negative log likelihood by that reward. And so if the reward is high, the model is going to be more likely to generate this same sequence in a similar context in the future. If the reward is low, it will be less likely. But this sort of brings up a natural question, what can we actually use as a reward to encourage the behaviors we want in this text generation system? That's really up to you as you design your generation pipeline. A common practice in the early days of using RL for text generation was to set the reward to be the final evaluation metric that you were going to evaluate on. And so here, instead of having a unique reward for each generated token at every time step, you would just take the final sequence score that you get and reward every token in the generated sequence with that value. And this was absolutely magical. You would set your evaluation metric as the reward, and you'd end up learning to get more reward, because that's what RL algorithms do, which in turn means that you were learning to generate sequences that do better on your evaluation metric. So NLG benchmark scores were shooting through the roof. We were making real progress. But it was actually all a lie. Turns out, as I'll talk about later, evaluation metrics, particularly for text generation, are just approximations. And it's not always clear that optimizing to those approximations is going to lead to more and better coherent text generation. Instead, oftentimes what ends up happening is that it just learns to exploit the noise in the evaluation metric. And in fact, in their large work where they introduced Google's neural machine translation system in 2016, Google researchers generally found that training machine translation models with RL and BLEU scores as rewards didn't actually improve the translation quality at all, even if it did lead to higher BLEU scores. But so designing your reward function is a very important problem in RL for actually learning the behavior that you want. And I've listed some cool work here on how you can actually learn to tie fairly complex behaviors to reward functions by actually initializing the scores that you use as rewards as neural networks that get trained on an auxiliary task ahead of time, but can then be used to provide scores as rewards to the system that you produce. So to go back to our example earlier of trying to create a dialogue agent that is very positive and only says positive things, you could use a sentiment classifier to produce a reward for the sequences that you generate. And so that's a lot of fun. Unfortunately, despite all the fun that you can have using RL to train text generation engines, there's a bit of a dark side too, which is that reinforcement learning algorithms can be notoriously unstable. And so to get these text generation systems to learn with RL, you often have to be thorough in tuning different dials in your model setup accurately. There's many of them. Two of them that I think are worth mentioning are one that you always need to pre-train with teacher forcing. You generally can't train with reinforcement learning from scratch. And also you need to provide some type of baseline reward that your model should be achieving. So for example, BLEU score, which I described earlier, is always a positive value unless it's 0. But that means that if you use it alone as a reward, every single sequence that you sample ends up, being encouraged in the future. So what you want to have is some type of baseline that is an expectation of how much reward you should be getting, which can be subtracted from the reward that you actually get, so you can discourage certain behaviors as well. One last note about this is that neural networks are quite good at finding the easiest way to learn something. So, if there's a way to exploit your reward function, it'll find a way to do it, particularly that's easier than learning the behavior that you want it to learn. So it's something to remember that's kind of important if you try to use reinforcement learning for text generation systems, particularly because there's such a large action space of words that it can generate to try to accomplish certain behaviors. So, to end this section, I just want to start off by saying that in general, we still use teacher forcing as a primary means of learning to generate coherent text. It has diversity issues, but it still lets us learn a model with decent text generation abilities. One thing I haven't focused too much on in this lecture is the type of model that you can use to actually generate text, because they tend to be less universal and much more designed to very specific end tasks. But in general, a common approach in NLG is to try to design a neural architecture that allows your model to be perhaps less sensitive to the problems of teacher forcing, or to address them with additional loss terms that are perhaps task specific. Exposure bias, though, is a problem everywhere, pretty much regardless of your neural architecture. And to kind of mitigate it, you can either train your model to be more resistant to its own distribution changes through things like semi-supervised learning, or you can change your pipeline such that you're learning to make modifications to an existing sequence that you retrieve from your training set, rather than trying to learn how to generate sequences from scratch. The caveat there is that, as the type of text that you're generating gets longer and longer, doing this kind of retrieval and editing becomes just as challenging as generating from scratch in many cases. And finally, you can use reinforcement learning as another means of learning from your own examples. And in effect, you can also use it to encourage different behaviors than just likelihood maximization. But this type of learning can end up being quite unstable. And unless your reward is well shaped, the model can often learn to exploit it.
Are there so online language simulators where you can train with RL online, or are you only talking about training offline?
No, in this setting, we're generally talking about training offline. So you train it all ahead of time, and then you use your model as it's been trained the first time around. Okay, yeah. So now we've finally reached the section that I hinted at earlier on a very important topic, evaluation, which, to be honest, is something that we should be thinking about before we even start designing a model or a training algorithm or a decoding algorithm. It's, how can we actually check that our method how are we actually going to evaluate that our method is even working? And today I want to talk a bit about three types of evaluation metrics. So first, we'll talk about automatic eval metrics, because generally you need to be able to rapidly prototype and diagnose failures in your model. So it's essential to be able to have this quick feedback, even if it's very coarse. And in automatic evaluation metrics, we've traditionally used what I'm calling content overlap metrics, which focus on how much a sequence explicitly resembles another sequence, usually in terms of word or phrase matching. Lately, there's also been new automatic evaluations that are model-based, where we try to use advances in embeddings and neural models to define more implicit similarity measures between sequences. And finally, we'll talk a bit about human evaluations, which are kind of the gold standard of evaluating text generation. But they also do have downsides that we'll get to as well. And I just want to note that some of these slides here are actually repurposed from slides from Asli Çalık-Yılmaz, who's a leading expert on NLG evaluation. But so let's jump in. So content overlap metrics generally compute an explicit similarity score between two sequences, the one that's been generated by your model and some gold standard reference sequence that was attached to the inputs that you had. So in other words, a sequence that was an appropriate generation for the inputs you had. And these metrics are often a popular starting point because they're fast and very efficient, which is their main benefit. As long as you have a reference sequence to compare to, you can compute these scores rapidly to get feedback. And I'm going to categorize them into two zones here. First, n-gram overlap metrics that compute different functions of word and word-alike overlap, and semantic overlap metrics, which involve more complex overlap functions based off semantic structures. Unfortunately, besides being fast and efficient, most n-gram overlap metrics don't actually give you a great approximation of sequence quality a lot of times. They're already, not ideal for something like machine translation, where there can be multiple ways to translate the same sequence with things like synonyms, and they get, progressively much worse for tasks that are more open-ended than MT. So, for example, in summarization, the longer output texts make it naturally harder to measure something using word match. And in something like dialogue, it's incredibly open-ended. And in fact, you can have multiple responses to a particular utterance that mean the same thing, but don't use any common words. And so we can illustrate this with a simple, fairly contrived example where you have a dialogue context utterance that asks a question such as, are you going to Antoine's incredible CS224N lecture? A completely unbiased reference text from derived from a human, and then a dialogue agent that spits out different answers such as yes, which gets a pretty high score on our n-gram overlap metric, or it, which already scores a lot lower, despite depicting the exact same idea, or yup, which actually gets a score of 0. Meanwhile, a completely incorrect answer, heck no, gets the highest score out of all of them, which kind of points to the issue. When you use n-gram overlap measures in a lot of applications, you're going to be missing the salient elements of what the generated sequence should capture, and instead, be getting stylistic similarities between texts, even as you miss the most important context. And if you prefer empirical validations to contrived examples, it's actually been shown that many dialogue evaluation metrics don't really correlate well with human judgments at all. And this gets worse as your sequence length increases typically. So with an open-ended task like story generation, you can get improved scores by just matching a whole lot of stop words that have nothing to do with the content of the story itself. We also have another category of overlap metrics that I'll call semantic overlap metrics, because they don't necessarily tie directly to the words you used, but instead try to create conceptual representations of the generated and reference outputs instead. So the center one here, Spice, for example, creates a scene graph of your generated text, and then compares that to your reference caption to see how similar this more semantic representation ends up being. But clearly there's some limitations to how well explicit content overlap metrics can do, particularly as we start thinking about more open-ended tasks. So in response over the last years, there's been a focus on using model-based metrics whose representations come from machine learning models, and where they can be used to actually evaluate the fidelity of generated text. And these are nice because there's no more needing explicit matches between words in your reference and generated text. Instead, you can rely on much more implicit notions of similarity that you get from word embeddings. And so, there's been a lot of models developed in this area. Some of the original ones kind of focused on, defining composition functions over the embeddings of words in your generated and reference sequences, and then computing a distance between the compositions of the two sequences. Some more, some more involved takes on this idea are things like word movers distance, where here you actually try to map word vectors in both your generated and reference sequences into pairs with one another. So each word vector is paired to another word vector in the opposite sequence, and the distance between them is computed. And then you allow the evaluation metric to actually compute the optimal matchings between these pairs of words, such as the total distance is minimized. And BERT score, which has become quite popular over the last year or so as an evaluation metric, is pretty much just word movers distance, but using contextualized BERT embeddings to compute these distances. Sentence movers similarity is kind of another extension of word movers similarity that adds sentence embeddings from recurrent neural networks to this distance optimization, and that allows it to be more effective for evaluating, let's say, long multi-sentence text as opposed to just single sentences. And finally, last year, there was a new model named BLERT, which is actually a regression model that's based on BERT. And here it takes a pair of sentences, the reference on the generated one, and returns a score that indicates to what extent the candidate is grammatical and conveys the meaning of the reference text. So we can talk about a lot more evaluation metrics that are computed automatically, and there's far more of them than I actually mentioned, though they do tend to fit in those two categories that I described. But it's important to remember that at the end of the day, the true mark of an NLG system's performance is whether it's valuable to the human user that has to interact with it or read the text that's produced from it. And unfortunately, automatic metrics tend to fall short of replicating human opinions of the quality of generated text. And that's why, for this reason, human evaluations are viewed as the most important form of evaluation for text generation systems. Almost all work in NLG generally includes some form of human evaluation, particularly if the task is more open-ended. And if it doesn't, well, let me be frank, you should probably be skeptical of any claim that's being made by that work. And finally, another use of human evaluations is that in addition to evaluating model performance, you can also use them to actually train new machine learning models that are meant to be evaluate, that are meant to serve as evaluation scoring functions themselves. I guess the main thing to mention about human evaluations, since we could talk about them for a while, is that they're both very simple but also very difficult to run. They're simple because you generally just need to find judges and ask them to rate an intrinsic dimension of the quality of your generated text. So you have to define a set of criteria that you decide is important for the task that you're designing a system for. And that can be things like fluency, where you just measure things like grammar, spelling, word choice. Does this actually look like human language? Factuality, does the text accurately reflect facts that are described in the context? Common sense, does it sort of follow the logical rules of the world that we might expect? But once you've defined these criteria, you can have humans evaluate the generated text for how well it actually produces text that caters to these particular criteria. One thing to note here is that while these dimensions are common and repeated across different evaluations, they can often be referred to by other names and explained to evaluators in different terms, and be measured in different ways. And in fact, one of the problems with human evaluations is that across works they tend to be very unstandardized, which can make the replication of human results quite difficult. And that's why when you read text generation papers, you rarely see a comparison of human evaluation scores between two different studies, even if they evaluated the same dimensions. But another set of issues with human evaluations, beyond the fact that they're slow, expensive, and unstandardized, is that humans themselves aren't actually perfect. I guess there's a few negatives that I can say about humans. Even though we're all humans, is that we tend to not be very consistent folks. Often changing our minds about how we view something, depending on something as trivial as the time of day. We don't always reason in the way that we're expected to when presented with a task, such as evaluating something. We can lose concentration and not really be focused on what we're doing. And, we can often misinterpret what, let's say, a human evaluation is asking us to do, such that we inject our own biases into the task. And, on top of all of these things, when we run human evaluations, we're also dealing with the fact that one of the big motivators that our human judges have is to do the task as quickly as possible, which isn't a great mix, particularly if we want them to really give us high quality ratings. But humans are kind of the best thing that we have to actually give us the most accurate assessments of whether text generation systems are doing well. So we do the best that we can. I'm actually gonna skip this slide, but I mentioned earlier that one of the things that we can also do is use human ratings to train models to actually predict scores for text itself. And so two systems that do some things along these lines, I've provided citations to here so that you can take a look at them if you're curious later on. But so, the takeaways that I kind of want you to get from this section are that, evaluation is quite hard, and particularly in text generation. So content overlap metrics do provide a good starting point for evaluating the quality of generated text. If you run these n-gram overlap metrics and they show scores that are worse than they should be, that's the first sign that you have a problem. But they're generally not good enough on their own. Model-based metrics tend to be more correlated with human judgments than content overlap ones, particularly as the tasks become more open-ended, such as dialogue and storytelling. But the downside there is that they're not very interpretable. Unlike with a content overlap metric where you can say exactly, oh, this is why this score is this way, it's because these words match up with these words. With a model-based metric, you get a much more implicit definition of similarity, which while useful is also less interpretable. Human judgments are absolutely critical because even if they're inconsistent and sometimes don't do the task that you want them to, humans are actually able to intrinsically evaluate dimensions that we don't even know how to formulate using any type of automatic metric. But lastly, slightly unrelated to what I've spoken about in this section, I just want to say that the number one evaluator of any NLG system that you create should really be you. A look at your model's outputs as perhaps you do a project that involves NLG can really be worth days, weeks, and sometimes months of staring at evaluation metrics that are perhaps a bit uninformative. So if you design NLG systems, make sure to evaluate your own generations very consistently. So in this last section, I think it's quite important to talk about ethical topics in natural language generation as well, because ultimately, while NLG really allows us to tackle new and interesting applications, if we're not capable, we can end up deploying fairly dangerous and harmful systems. And as a warning, I just want to say that some of the content on the next few slides can, is going to potentially be quite uncomfortable. But I think it's important to make very clear how these systems can go very, very wrong. And without picking on a particular example, I do perhaps think that one of the most famous examples of this was the Tay dialogue chatbot, which was released onto Twitter in 2016. And within 24 hours, it had started making some very nasty comments that exhibited racist, sexist, anti-Semitic, white supremacist leanings, which is ultimately probably not what the designers of Tay had in mind. So what actually ended up going wrong with Tay? Well, here's the thing: Tay behaved exactly as we should have expected it would. It was designed to learn to exhibit the conversational patterns of the users that it interacted with, and it did that. NLG models are very good at capturing the language distribution of their training examples. That's been the one thing that we've been remarkably consistent on over the last few years. And it turns out if their training examples end up having toxic content, they will learn to repeat that content. And this is perhaps no clearer than if you look at what pre-trained language models have to say about, let's say, different demographics. So if you remember, large pre-trained language models that underlie modern NLG systems, they're trained on massive corpora of text, which are often opaque and crawled from online resources. If it turns out that those corpora have toxic content, the language models are going to learn it and in fact make it even worse. And then it turns out that if you prompt these language models for certain pieces of information, it can spit out that toxic content, showing very different opinions across gender, races, sexual orientations. Now, I'll concede that it would actually be rare to ask a language model to weigh in with their opinions on this matter. But you do have to ask yourself, if this type of information is encoded in the model in some way, in what other ways could these learned patterns end up being reflected by this model once it's actually deployed in practice? And that kind of leads us to the second problem with these language models. We actually don't really know how information ends up being learned and encoded by them, which means that we don't have a rigorous understanding of what types of inputs are going to trigger what types of outputs. And in fact, Wallace et al. Showed in their EMNLP 2019 work that this was a big problem, because if you prime these models with particularly adversarial inputs, they would generally devolve immediately into producing very toxic content. In other words, what it took Tay 24 hours to learn how to do, these systems can kind of do out of the box if primed with the wrong examples. And unfortunately, the wrong examples, end up, being a lot less nasty than we might have expected, a lot less nasty than the ones on the previous slide, at the very least. But in a work at EMNLP findings last year, a research group showed that much more innocuous looking inputs could actually prime these language models to go on pretty toxic diatribes as before. It wasn't as consistent as in the previous work, but it was still often enough. And these examples really go to show that we need to be careful with how these systems are deployed. If you have an NLG system, you need safeguards to stop it from outputting harmful content. And this goes beyond the examples of toxicity and bias that I've shown today. A model that can be primed to generate incorrect or unfactual information can be quite dangerous too. And also, NLG models shouldn't be deployed without an understanding of who its users will be. And there's always going to be adversarial users for any model that you create, even if you can't think of them in the moment. And that leads us to the final point, which is that the advances in NLG have really allowed us to build text production systems for many new applications. As we do this, though, it's important to ask, does the content that we're building a system to automatically generate, for easy human ingestion, does it really need to be generated automatically? And I think a good example of this is the work of Zellers et al. At NeurIPS 2019, which showed off the potential dangers of fake news generators from pre-trained language models. I actually thought this was a great work, and it highlighted many of the defenses that you could be developed against fake news generations system. But the point is more so that you should always imagine that any tool that you create could be used in a negative way. So a storytelling NLG system can also potentially be repurposed to do fake news generation. And you should really always ask yourself whether the positive applications of a particular technology outweigh the potential negative ones. And that turns out to often not be an easy question. So I guess as concluding thoughts for today, I just want to mention that if you start interacting with NLG systems in practice, you're quickly going to see the fairly large limitations that they tend to have. Even in tasks where we've achieved a larger amount of progress at building systems that can do the task fairly well, there's still a lot of improvements that can be made to make them even better. In pretty much any NLG task, at the same time, evaluating it effectively remains a huge challenge. We often have to rely on humans to give us the best estimates of how well our system is doing. And so an area where a large improvement would really, kind of bootstrap larger improvements in many other areas of NLG would be to find better automatic evaluation for NLG systems. On the other hand, on a very optimistic note, I do want to say that with the advent of large-scale language models, deep NLG research hasn't been reset, but it's never been easier to jump in the space and start playing around with these systems and designing cool new tools that can help humans ingest content and information more rapidly and more efficiently. And as a result, I think that it's one of the most exciting areas of NLP to work in. And I think that if you start working in it as well, you'll feel the same way, and I would encourage you to do so. So thanks a lot for having me today. It was really exciting.